Okay, everybody, question came up. Oh, by the way, this is Dr. Thompson. I don't know if perhaps you haven't met him yet. Dr. Thompson helps us with the teaching labs and the demonstrations. So I wanted to, by the way, answer a question about the homework. We have a test on chapter 1 on Wednesday in class, brief, not very long. It won't involve any calculations. There will be things like the de Broglie relations and the wavelengths and momentum, for example, but not any detailed calculations like you had on the first two problems for today's homework. So don't worry about. Don't understand all the details. Don't worry about that. Okay, so we have another demonstration. This one is not specifically quantum, but it will help you to understand part of the experiment that is quantum. This is a laser, which is pretty easy to find these days. And there's a very small slit. So here's the laser. There's a little wheel here with some different size slits. And you can see the pattern here. So the slits are vertical. The slit is vertical, so light has to pass through a narrow region. The width of the slit has to be comparable to the wavelength of the light to get this sort of diffraction pattern. And so this is like the water waves I illustrated in a picture. Right. And so we can change the width of the slit here. And by changing the width of the slit that the light passes through, you can see the effect on the diffraction pattern. There is a maximum right in the center, and then off to the side there are these dark areas. So you get this set of fringes that correspond to maxima and minima in the light intensity. Okay. Yes.
Is the width like the separation between those lights?
Oh, the width.
The width it's inversely proportional to the diameter.
The separation between these minima is inversely proportional to the slit width.
Okay, great.
So as I decrease the width of the slit, I make it narrower, the minima move out. Reverse what you might think. That's characteristic of diffraction. So now I'm increasing the slit width, and the minima are moving in. Yes.
The minima are the dark spots, the maximas the green spots, correct?
Yeah, that's right. And, and notice if you just follow the dark spots, you might expect a dark spot right here. But that central one is not a dark spot, it's actually a maximum. So there's a pattern of dark spots, except extending that pattern of dark spots, you would expect a dark one right here. The middle one is actually a maximum. It's the strongest one. So you can, and that maximum occurs right along the line of sight of the laser. The laser is moving straight through, and if I took the slit away, this laser spot would show up right here.
I want to make sure I understood that, Dr. Dow. So the brighter spots are the maximas, and the darker spots are the minimas.
Yeah. Right.
Yeah.
Right.
No. I thought otherwise. I apologize. Sorry.
You see the dark spot pattern?
That's right. It is.
And if you marked off the dark spot pattern, and if you extended the dark spot pattern inward, you would expect another dark spot right here. Instead, right in the center, you get a maximum. And in fact, it's the brightest maximum. Okay. That's just kind of strange. That maximum in the center is exactly where the laser beam would go if I took the slit out. Okay, no slit at all. Okay. And notice the characteristic. Which way? Okay, so which way am I changing the slit? Is it going smaller? And the maximum are moving, the peaks are moving out. Minimum, maximum, doesn't matter. They're all moving the same way, right? And this central peak is getting broader as I decrease slit width.
This is double slit, right?
Single slit.
Oh,
Single slit. Just one slit. This is just regular, ordinary diffraction. This is the same pattern you would get if you sent water waves in your bathtub to a slit. You would get on the far side, you would get the same pattern if you have a quiet bathtub. Okay, this is diffraction of light. This is not really a quantum effect. This is purely what happens when you send a wave to a barrier with an opening. Happens with sound waves. We can do this same experiment with sound waves. It's a little more challenging, but you can do it. Yes, sir.
Pardon me, Dr. Dow. So why is there a dark spot if it's just a single slit?
That's diffraction. So to explain why this works, we would have to study the details of the particular physical phenomenon, in this case, an electromagnetic wave going through a region where there is an opening. So we would have to solve, to really understand this, we would have to understand the wave equation, which we will study here in a little bit, the wave equation, but we'd have to go back to electrodynamics. The wave equation would then be the propagating of a wave, but there's this barrier that has to be included in the wave equation. And that would then allow only solutions where the waves are coming out like that. But there's, in addition to this pattern that I'm showing, there's the diffraction. So this front doesn't have uniform intensity across. In fact, it would have that kind of pattern. Yes, sir. Mr.
So
Cameron.
really the only reason that there's diffraction is because the slit is so small that the laser passing through it. So if the slit was big, the laser would just go straight through and be a single point. Correct?
Yeah, that's right. Let's try that. So let's see. I'm increasing the slit width, right? Oops, went too far. Okay, so these are getting dimmer out here. You see the dots are getting, the minima are getting closer together. This is getting stronger, and if I could continue it, it won't let me continue the adjustment. But if I keep making the slit wider, this will become all there is, and it's just dark outside here.
Would the single point, if you did make it wide enough, would the single point still have, like, if we could see smaller portions of it, would it still have little?
Yes.
So even though it's passing straight through and not really hitting the slit.
Well, no, it would be hitting the sides of the slit. So the pattern will get narrower and more intense, but the little fringes are still there as long as it's passing through some finite width. And as you continue to increase the width, the sides of the slit still have some influence on the light passing through. Okay. This is going to be smaller, narrower, and taller. And so it's going to be harder to see the fringes. They're going to get tighter and tighter. But as long as it's passing through a slit, you get this diffraction.
So even if I open the door and I shine that same laser through the door,
Yes, sir.
even though we can't see it necessarily, but if we could, it still would be
You
there.
could detect it if you had a very sensitive detector. It would be a very small deflection angle because of the diffraction. Yeah. Yeah, it's neat.
That's cool.
Okay, but here comes the interesting thing. All right, so I'm going to turn this over to a, okay, there's a specific width of the slit, single slit still. Now I'm going to take two slits of the same width, that same width, and the two slits will be pretty close together. Okay, so here's the slit width, and this one is going to be the same width. And then there's going to be a separation between the two slits. And I'm going to move the separation, change the separation, holding the width fixed. And remember, there's also a third characteristic, which is the wavelength of the light. So I've got three distances, three lengths that I'm comparing. Everything is relative to those, to the wavelength of light. Okay, so there we go. Okay. Look at that. There are two links involved now. I don't know, can you see this in the back of the room? There's a very fine sequence of dots, minima. And then there's an overall pattern in between where there's also a minimum. So we replaced the single slit diffraction pattern. So here was the single slit diffraction pattern. Okay, and this separation was uniform all the way out. And this one would have been another minimum, except it's actually the maximum. The central peak is not a minimum, there's a maximum. Okay, now when we have the double slit, we get a combination. There's another pattern going on inside that's using. So the pattern has two cycles going on at the same time. There's another sequence of minima. There's an overall envelope, which is the original single slit diffraction pattern. So inside of the original single slit diffraction pattern, I get a finer gradation of dots. So this separation here was determined by the slit width. And this separation is determined by the distance between the slits.
So even 1,000 slits, you would still have the maxima at that one point.
Yes.
But you would just, all you would do is just keep making smaller and smaller waves all within.
Very
whatever.
good. Very good. Yeah. Yeah, you're trying to go to the south. I'm still trying to digest too. You want to go to the south. Okay, so now what am I changing here? Changing the change the width of the I'm sorry, the separation.
Separation, that wire separation.
Let me get out of the way.
Actually, this is split width.
I got the wrong one.
All right, no. These two splits varying with increase in split width or split separation.
Go ahead.
We got increased split separation.
Okay, changing split separation. Yeah. Okay, so
They came closer or?
these dots are merging. They're going so close together, it's hard to see the difference between them. So what you did was
This is
you start off increasing the slit width, right? Because you're getting these smaller dots are merging.
yeah. So I'll change the D.
This is the slit separation, not the.
Yeah.
Yeah.
Holding the width of the slits the same, just moving them farther or together apart. Okay. Is there a multiple one on there? Just for grids?
There,
Thousand.
You got around. There's two, there's three. 4. Yeah, but the problem is the split widths and the separations are all losing. You're just increasing the number, but keeping the distance and the widths.
5.
Okay, so you get I think we're not controlling everything.
yeah, that's the whole thing.
Yeah, so to do your demonstration, I don't think it's on.
You'll be in the last.
Okay, so the point is that the double slit has this very interesting interference pattern. And there are two characteristic links of this interference pattern. There's this overall, I call this the envelope. Overall minima determined by the envelope, and this distance is determined by the widths of the slits. And then there's a separation here between these minima inside of the envelope. And that separation is controlled by the separation, the distance between the slits. Okay, interesting enough, right? But this is not quantum. This is diffraction. You could do the same thing with water waves. You could do the same thing with sound waves. Anything kind of wave will have this behavior. It's just the reason that we use a laser is because the coordination, the coherence, talk about the coherence of the light, which means as the light is going through, that the wavefront is, if it's a maximum here, it's also a maximum over here, and the wave is just going through. And also that the distance from one peak to the next peak is exactly the same all the way through the wavefront. It's a very coherent source of light. Sunlight is not coherent, so it would be difficult to, you would get this pattern, but it would die off quickly away from the central peak. You don't get a nice pattern like this because it's not coherent. So that's why we use the laser for this demonstration. Okay, so I'm going to talk about this here in just a minute. I'll let Dr. Thompson go ahead and move this. Thank you. We're going to do the same thing now, but make it into a quantum experiment. And this is where things get really interesting and really relevant to quantum mechanics. Yeah, let's turn it back on. Please.
So would any light spot ultimately have fringes because
Say again.
would any laser, even if it's not passing through a
Hang on a
state?
second. Hold on, everybody. I'd like everybody to hear the question.
So let's say there's a beam of light going, and if you put it on a screen,
Yes.
even though it's not, it looks like you're not passing it through the slit, it's still sort of a huge slit that it is passing through. Imagine it
Yes.
could be. So if you zoom in and look deeply,
Yes.
no spot of light would be continuous.
Right. You'll see that if you look carefully enough at any light going through an opening, there's a diffraction, even if the opening is quite wide compared to the wavelength. There's still, but it's very difficult to detect.
So what I'm saying is any light, even if it's not going through an opening, it's going from one spot to another spot, you could think of it as, because it's always going between physical things, right?
There's diffraction around objects.
Yeah,
Yes,
yeah.
that's true. Yeah. And it doesn't just happen if you have a slit. Also, we could do the opposite. We have a barrier passing the light through, instead of a slit, we have a barrier. And then you get light passing on the outside. You also get a diffraction around the edges of the object. And so if you had light coming by a barrier like this, and then look out here, you'll also get diffraction of the light past the edge, the knife edge. Look at a knife edge with a laser. Could have just done a knife edge, passed the laser by it. You'll get light diffracted around this. Knew about this, and did quite a lot of work on the diffraction of light, even in those early days before you understood electromagnetic waves. The light diffracted around sharp edges. Didn't have a laser either. Yeah, it was pretty good.
Is that, so that's all that's included in the study of like optics, for example?
Yes, exactly. Part of optics, maybe you haven't studied, is diffraction. And this is called classical optics. There's the ray tracing that you see through lenses to figure out how lenses will magnify and so forth, change the images. But there's also diffraction of an object if you have in a telescope a finite size area, say a mirror or a lens, the light's passing through, causes diffraction. And so there is, when you look at a telescope, there is a diffraction of the stellar image because the light is passing through an aperture. And the limitation of the resolution of the telescope is determined by that size. And this is different than magnification of a telescope. Just having a finite size limits the resolution of the telescope. And that's why small telescopes have less clear images than big telescopes because of the diffraction effects. And so this is an important effect in optics. Yeah, Mr. Campbell.
So I have a telescope and it's not very long. It's probably only about this long, but it's fairly wide.
Yeah.
So is that, if it was longer and still say the same width, would that increase resolution, or is it more about the fact the aperture is of large diameter?
I'm not sure how the relationship, I mean, the diffraction always occurs, and it's the primary factor is the size of the aperture. Now, is making the focal length longer, does that improve the resolution?
Yeah, I guess that's what
I'm not sure. I have to think about that. I don't want to spend too long talking about classical optics. I'm trying to get to the quantum thing here. If you're interested in diffraction, let's talk after class. But the point is that we're going to be, this is one of the experiments that reveals quantum nature. So if we take that laser and turn the intensity way down, instead of using our eyes, we have some kind of tube, some kind of detector that can pick up on very low intensity light. That's one of the experiments that we're going to talk about. So you're sending small amounts of light through at a time. The other one, which gives a even more surprising result, is to do this with electrons. So we have an electron beam sent through a double slit diffraction pattern. And this is the classic double slit interference experiment. And remember what happens. So I'm going to talk about what happens here. Well, actually, let's go back. No, I'm going to talk about this here. So let's go ahead. Okay, so we went through the review of classic quantum experiments that were done about 100 years ago, revealing that something was going on in these certain situations that could not be explained by physics that we understood up to that point. Something new is happening. So we have to be very careful about our conclusions about these experiments. For example, the atom, when we're looking at properties of the atom, we have to be very careful because we don't have, there we go. Hang on, I got to get my settings right up here. That's not the one I wanted. Here we go. There we go. Okay, so an atom is not something you have personal knowledge of. You don't have proper knowledge of an atom. I say that with high probability. It's not that you couldn't, but just that none of us have done what would be required for you to really know an atom. Very difficult experiment. In fact, I don't know anybody personally who could reasonably claim to have that kind of knowledge. What we have is very indirect knowledge. Okay, so, but it's clear that something is going on that isn't described by Newtonian mechanics and also Maxwell's equations. But we're going to focus on the first one, on the Newtonian mechanics. So we find out that light is emitted and absorbed by atoms, apparently in lumps. And this is not explained by understanding how charges would be influenced by an electric and magnetic field. Something is going on beyond what we have studied so far. And so that leaves us with the question, this occurs, it's clear, but what is the conclusion to be made from that? Is it true that the electrons, that is the electron orbits in the atoms, are quantized? Is the light somehow quantized? Or is it both somehow acting jointly? Be very careful about how to approach this. With remembering our goal always, to understand what's going on, not just to derive some kind of set of equations which somehow governs and matches the experiments. So a mathematical formalism, even a successful one, especially a successful one, actually, will lead us to a deeper understanding of the physics. So we don't just stop. Once we have the equations, we're not going to just stop. So we're not going to be satisfied with just having equations that can be used to compare to experiments. We want to dig through the meaning of the equations and understand what we've learned real about the physical world through the equations. You remember that? We want the equations there. We want to see the world through the equations. We don't want just there to be equations and nothing else. Okay, so there was the Bohr-Sommerfeld condition. In the early days of quantum mechanics, Bohr and Sommerfeld came up with this idea based on classical mechanics, that if I integrate the momentum around the circumference, suppose I have a circular orbit for the electron going around the proton, well, that the integral of the momentum going around the circumference has a particular value. It's called an adiabatic invariant. It has a significance in classical mechanics, planetary motion, for example. They said, well, this adiabatic invariant should come in lumps. Why? Don't know. But if we do that, if we require this, then we get some interesting things that's related to the idea that the angular momentum should be come in lumps. Okay, remember the angular momentum is a product of the momentum and the distance involved. And classical rotating objects can have any degree of angular momentum. But suppose we require that for the electron and the hydrogen atom that this angular momentum should come in lumps of h, where h is Planck's constant. Okay. And so this, let's do some dynamics, and this is related to your calculation on the first problem. It was first or second problem today. So if you didn't fully understand that, it's okay. Study the solution I'm going to send out. And I'm not going to require that you be able to reproduce these details. The details of this calculation will not be on the test, but I want you to understand generically what's going on. So the energy is a combination of kinetic and potential energy. So for the electron and the proton have the opposite charges, the potential energy is negative e squared over r, or just two charges a distance r apart. Okay, and the angular momentum would be the momentum times the distance. And let's suppose that that's comes in some multiple of h bar. So little l here is an integer. We require this, which you know from classical mechanics, and this additional piece. What's going to be different then? Okay, so after a little manipulation, you find out that the energy has to be proportional to 1 over L squared. And L is an integer. Well, L equals 0 doesn't work. But L equals 1, 2, 3, 4 is, let me tell you the significance of this then. If we have a set of energy levels in the hydrogen atom, then light coming in could cause an excitation, making the electron move from one orbit to another orbit. And that would correspond to absorption. So the difference between two levels would come out to correspond to the absorption spectrum. Or if an electron is in a higher orbit and falls down, it could emit light. And again, that light would correspond to the energy of the light, would correspond to the difference in energy levels. And so that would correspond to an emission spectrum. The unit here is a Rydberg. It comes from the basic constants. Mass of the electron, the charge on the electron and the proton, and h bar. Planck's constant. Okay, this is hand waving, right? They're just trying to figure out something, see if they can get anything to work. And actually, the energy scale works. This does match the energy scale and the energy differences match the values observed for the hydrogen spectrum. Odd. Don't understand this. This is hand waving. But this is how the imperiometric goes. You try things, maybe you don't fully understand what's going on. If it works, then you start trying to figure out what does that tell you. It may still be wrong. It may be coincidence that came out. Yes.
So that when you're saying hammer, they were just randomly, they were just not randomly, but they were guessing. They were just guessing.
Yeah, it's a guess.
And this happened to be that.
But it was an educated guess. I mean, I'm not giving you the reasoning behind your guess.
Yes, sir.
This adiabatic constant comes from understanding orbits of two particles that are attracted to each other. And there's a lot of theory relating to this adiabatic invariant. So they thought it would be a simple thing to work in terms of this adiabatic invariant. If the energy is quantized, it means this adiabatic invariant is quantized. Maybe that would happen if the angular momentum is quantized. That's their thinking. So they're taking quantization of energy. Let's work backwards. They're assuming that the orbits are quantized, so the electron and the electron and the hydrogen atom is quantized. What does that give us? It kind of leads us to the conclusion maybe the angular momentum is quantized, and in fact leads us to this, which somehow corresponds to the spectrum of emission and absorption by the hydrogen atom. It's not a clear theory. This is hand waving, right? But this is, you're going beyond what you know here. The imperiometric is helping you get some stuff, but it's not clear yet what's going on. Okay, so anyway, these correspond to these spectra. These energies, the differences between these energies correspond to the hydrogen emission and absorption spectrum. And the Rydberg is the energy scale. That seems right. The Rydberg looks right because the colors are right. The frequencies come out. Yeah.
So the equation saying that the more energy levels it goes across, it's less energy required to do that.
Yeah, that's right. Correct. Yeah. So this energy spectrum starts off at the lowest level. It's not L equals 0. That won't work. But L equals 1 is the deepest one. And then there's another one. And so they're accumulating. So L equals infinity would be 0. That would be for the electron to be far away from the proton. And so this is the L equals 1, L equals 2. And so we would say maybe I can excite the electron, and so I would get the hydrogen atom would absorb light from what's coming through. And so it become excited, so that's an absorption, or hydrogen is somehow excited because it's hot. The electron jumps down to the lower level and emits light. So it's these energy differences that are apparently correspond to the spectrum. It's not right. This is wrong. But it's got something right about it. Mainly, it's helping us to understand the idea of quantization of the electron orbit. Okay. Be careful here. It's clear that the electron is influenced by some kind of wave, because we have this kind of resonating structure that is set up. Okay, but electrons are not waves in the ordinary way that we talk about it. It's not like water waves or light is a wave. Electrons are not waves like that. They're particles. So something can't be both particle and wave at the same time. That would contradict the principle of contradiction. But you can't even imagine something that is both particle and wave. And in fact, there's a good reason, because that would be a basic contradiction. Something can't both be localized and extended at the same time. That means there's two things going on. There's a particle and a wave. Two entities at work in the hydrogen atom. Okay, so there's this interference that's going on, and this interferences would be allowed if there's a wave particle, a wave entity. Okay, so avoid the word matter wave, even though you've seen it. It's confused. What is the meaning of matter?
Potential.
Yeah, it's potential. Matter is the potential. That's what something can become. Matter. Something is changeable. It's a combination of act and potency. So matter is that changeability. So matter wave is fusion. Properly, we should understand the wave nature of massive bodies. That's the correct terminology. That massive bodies like hydrogen atom has both particles and waves involved in some way. But an electron is not a matter wave. That would be wrong to say.
So when we say particle, that I know it is a substance because it exists of itself. But when I say wave,
yeah,
usually, for example, we were looking at the light wave, that we look at as property.
That's right.
So is a wave, can wave even be put on the same footing as a substance?
No, it's not. It's a property of a substance. So, I mean, our example of wave has been, for example, the light waves are properties of the planet. Water waves are properties of the water. So the wave, whatever wave is involved here, is not, properly speaking, a separate substance, but it's probably, most likely, a property of the planet. Okay, and then we have this other thing, that there is some kind of guiding wave associated with the electron, and there is some kind of wavelength, because I could perform the double slit experiment, even a single slit experiment, on electrons, and I get the fraction of the electrons. That's weird. Okay, that's surprising. But it means there's something, not just a particle, but also a wave. There are two entities involved, a particle and a wave. And so this wavelength in the de Broglie relation tells you the wavelength of the guiding wave. Not the particle, but the guiding wave that is associated with the particle. So we're getting this picture that an electron is moving around under the influence of a wave. Now we see the electron, that's what shows up in the experiments. but it's being always influenced by this guiding wave that we don't see directly. We see only its influence on the particle. But it's always present, never goes away. And the de Broglie relation gives us some indication of the wavelength of this guiding wave structure in relation to the electron that has momentum p. Okay, so we should have this diffraction pattern, and this is observed. The wavelength that's associated here is the de Broglie wavelength. It's inversely proportional to the momentum of the electrons coming through. Okay, but it's not the wavelength of the electron, it's the wavelength of the guiding wave structure. So the guiding wave structure is actually the thing that goes through this diffraction. The electron is being steered. The electron goes through the slit and is being steered by the guiding wave structure on the other side. And so it will change the pattern of electrons on the screen, on the far screen, but it's not the electron that's being diffracted, but the guiding wave. Hang on. So if we do the double slit experiment with electrons, we'll get this pattern on the far side. And remember what's happening here. Okay, you have this. Remember what's happening. One electron goes through, we get a blip. Another electron goes through, we get another blip. Keep doing that, collecting more and more. And then you see this pattern, like we see for the light, but it's one electron at a time. It's very strange. But what's happening is that the electron is going through. When it goes through one slit or the other. The electron does not go through both, contrary to what you've heard. The guiding wave goes through both and is diffracted. And the diffraction of the guiding wave alters the motion of the electron once it gets through the slit. Okay. So to do this experiment, you have to have slits that are very narrow, right? Because you have to get comparable to the de Broglie wavelength and the separation between the slits. Yes, ma'am.
Can you explain the guiding wave more? Like if waves are properties of a substance, what's the substance that the wave is?
Quantum. Quantum. Quantum is the substance. Okay, who remembers what is quantum?
It's the non-massive substance.
It's the chargeless non-massive substance between massive bodies. It's one of the elements of the hydrogen atom. The electron and the proton and the planet are three parts of the hydrogen atom. You often heard it said that the atom is mostly nothing. That's not correct. Why do they say that? Because the electron is some distance out here, and the electron is, we don't know how big it is. It's really small. The nucleus, we measured the size of nucleus. Still very small. There's a lot of volume in here, but it isn't nothing. It can't be nothing. Nothing doesn't exist, right? It's something, and it's changeable. It's a physical substance. Okay, so the guiding wave is a property of the planet, just like electromagnetic waves are properties of the planet. Gravity is a property of the planet. And there are other fields too that we haven't talked about. This is another field. We don't know a lot about it. We do know some things, and this is revealing some of the properties of the planet, this guiding wave structure. Okay, so this is showing that there are two entities that are involved. There's not one that's both particle and wave. That makes no sense. You can't have something that's both localized and extended at the same time. Can't be. This means that there are two things going on here. That the guiding wave is going through the slits, and the electron is going through one of the slits, one or the other. And different electrons are going to go through different slits, right? Sometimes it'll go through the upper one, sometimes through the lower one. But it's always guided by the guiding wave structure, and the diffraction pattern on the far side is going to influence the motion of the electron after it gets through. And that's why it shows up like this. That's not really, I mean, it's surprising if you think about it, but it's not really a paradox, right? It's a surprising conclusion, logically obtained from the experiments. Okay, so there are two entities involved, the particle and the guiding wave. The guiding wave is only seen indirectly by its influence on the electron. We don't have detection yet of of the guiding wave directly. The guiding wave goes through both slits. Contrary to what you've heard or read, if you've read about quantum mechanics, the usual explanation is that the electron goes through both slits. Each electron goes through both slits. That can't be. That's a non sequitur. It's not a logical conclusion. It's illogical. And it's not necessary either, of course. One would be surprised to find nature making you think illogically, right? If you do that, if you do a whole bunch of calculations and show up 2 + 2 is 5, you don't think, look what I've discovered. You say, I have made a mistake somewhere. There's a logical misstep somewhere. And so this is a resolution of the problem. Yes.
Dr. Bell, when you say the guiding wave, I'm thinking, so does that mean, since the guiding wave must be property of, I'm assuming it must be the property of the quantum in some fashion, does that mean does it mean the electron has virtual quantum? You say it, but when it goes through, when you say the guiding wave goes through both the slits, does that mean the virtual quantum of the electron?
Well, we don't need to look at the virtual quantum of the electron. You mean the quantum inside the electron, right? That's what, I don't know what you mean. If you don't mean that, I don't know what you mean by virtual quantum of the electron.
I guess never mind then.
The electron is moving through the quantum.
Yes, sir.
And like any sort of electromagnetic waves, for example, in the quantum would influence the motion of the electron because it has charge.
Yes, sir.
This guiding wave is acting in a different way. It's not responding to just the charge because we can do this experiments with particles that don't have charge. We still get fraction. Okay. So it's not an electromagnetic wave, it's something else, but it's responding to the presence of the particle and it's influencing the motion of the particle.
And does that mean that the guiding wave must be in some way like a property of the quanta at all?
Yes, I've said that several times.
I'm sorry. I'm just trying to understand how.
The guiding wave structure is a property of the quantum.
Yes, sir.
That's very generic. We don't have a lot of specifics at this level here. Right? These experiments are not giving us a lot of specifics, but that's a generic thing. It must be property of the quantum.
And does that mean in any way, is that caused by? Is somehow in some way the electrons causing this guiding wave?
Ah, that's another question. Okay, does the particle cause the guiding wave? And the answer is it does, but there's also some part of the guiding wave which is not coming from the electron. So, okay. So we're going to find out that the guiding wave has two components to it. There's one part which allows a kind of resonating motion like the electron and the hydrogen atom. And that's explaining this kind of quantization of the orbits. And we'll see other examples where the electron confined to a volume can only occupy certain energy levels. And that's because there's a kind of resonating behavior of the guiding wave. Only certain modes of the guiding wave will be commensurate with the box that's being held in. But there's another part. Remember we said, why doesn't the electron spiral down and lose all of its energy and collapse onto the proton? Why is the hydrogen atom so stable? Even in its ground state, it doesn't lose any more energy. Once it's in that lowest level, it doesn't lose any more. Why is that? That's the other part of the guiding wave structure called the stochastic part. The guiding wave structure has some component to it that keeps kicking the electrons and keeps it from collapsing. So they're both present. The stochastic part keeps the electron from falling down any farther below this. But there's also a kind of resonance that goes on. If the guiding wave can be set up in a certain way, then it would be like a resonance. If you've taken a glass of water and swirled it, that's a kind of traveling wave. If the traveling wave can be set up, the guiding wave can be set up in a traveling wave like that, that might help to explain the orbits, the quantized orbits of the electron. So this is where we're going to go, but it's a very logical conclusion from the experiments. Yeah.
If you go to the diffraction patterns of the electrons that you showed on the electron microscope images, you don't see any substructure within each ring.
I think that was a single slit diffraction pattern. It does have a double slit diffraction
okay.
pattern. If you're doing a double slit, yes.
The double slit, you would see that.
Yeah, I think that illustration is a single slit diffraction. You're right. illustration doesn't have the double slit, so there's more structure to it, as you saw in the double slit with the light. Okay, so then the de Broglie relation with the Bohr-Sommerfeld would say that, and again, the Bohr-Sommerfeld condition that I showed you earlier is wrong. But we're kind of trying to roam around to find some kind of mathematical structure that will work. And so we have this resonance condition that the circumference is a multiple of the wavelength of the guiding wave structure. So the wavelength is determined by the momentum, and then we require that this invariant, then we work out what it is, and we say that this is quantized, and so that says that the radii of the orbits are quantized, so that the guiding wave structure fits in one complete cycle on its way around. It's wrong, right? This is not right, but it's the kind of hand waving thing that was going on in the early days. Okay, so that gives you quantization of the angular momentum. It's not right, but there's something that's sort of right. What's right is the resonating condition for the guiding wave. The details are not right yet. Okay, so de Broglie is then concluding that the quantization of the hydrogen atom is due to a kind of resonance of the guiding wave structure. This is back in the early 20s. Louis de Broglie was a French physicist who worked in the early days of quantum mechanics. And Einstein thought his ideas were largely correct. Something was missing, but it was largely correct. Okay, so 3 things to remember. Right, we're just at the beginning, trying to sort this stuff out, and there's a lot we won't sort out. So we'll get to some parts of it. In particular, what we're going to do is to study massive particles, like an electron, moving in different physical situations, like being in the presence of a proton. We aren't going to look at the other part. The other part of this problem is light itself appears to be quantized, and the constant experiment demonstrates that light has some kind of particle nature, but that's a later subject here. Okay, you're going to have to look later because it's more difficult at quantum field theory, which is the understanding of the quantization of the electromagnetic field. So we're not going to do that. We're going to take out of these experiments the ones that deal with an electron. And we're going to study that and see if we can understand just the quantum mechanics of an electron. And that's what we're going to do in this course. That second course, stay tuned. Okay, 3 things to remember in how we're going to be approaching this problem. Yep. Another 4 things. Yeah, you're right. Thank you. I made this change today. It should be 4 things. There are 3 things in the text. I added something.
A number of things to remember.
A number of things to remember. There are 3 things in the textbook. I added a 4th. Okay, the particle is guided by a guiding wave structure, details of which we don't yet know. The guiding wave structure can set up both an interference and resonant patterns, which lead to quantization of the electron orbit. So we're going to understand electron motion as being governed by this guiding wave structure, and that somehow it's going to be the resonance of this guiding wave structure that quantizes the motion of the electron. And this is going to explain, for example, the hydrogen spectrum. The last one is that quantum mechanics does not deal with individual particles. You saw I had to shoot one electron and another electron and another electron to get the interference pattern. Because if I just shoot one electron through, I just get one spot. To reveal the action of the guiding wave structure, to get a fuller picture, I have to have multiple electrons going through. I have to have what's called an ensemble. An ensemble is 1,000,000 copies. And I run each one through. I prepare each one in an identical way, and then I run it through and I collect statistics on the ensemble. I'm not just going to look at individual ones, but I'm going to look at the ensemble as a whole. Because if you only look at individual electrons, you don't get that interference pattern. It's only through doing the ensemble that the guiding wave structure is made clearer that's present. So this is very important. Quantum mechanics, in fact, what we're going to develop will not really apply to individual systems, but applies to ensembles and with statistical averages over the ensembles. So we're going to look at the average position for the ensemble or other measures of ensemble. So instead of saying, the class is half girl, half boy, I'm not going to say individually. It doesn't mean that each person is half girl, half boy, right? That instead, what we've got is we're going to look at statistical averages over the entire class. Okay. Also, the important thing, this is what I added this morning, I want to emphasize, particle cannot go through both slits. So it reveals that there is another entity at work in the diffraction, which must be then we call a guiding wave structure, which is then the guiding wave passes through both slits. And that's how we get the interference path. Okay, so two ways of thinking that we want to use. First is physical. That's always first. And by physical, I mean in relation to the basic things that we are sure about, those basic principles of physics that we talked about. And the second is imperiological. The Bohr-Sommerfeld condition, the de Broglie relations are just kind of hand-waving things. They're just getting some nebulous idea about what's going on. We're going to find that it gels into something that we're going to try, the Schrodinger equation. And the Schrodinger equation will make predictions that turn out to be in agreement with the experiment. We're not done. We have an equation. What does it mean? I don't mean what are the, how do you read out the solutions? I mean, physically, we have learned something from the imperiological that has taken us beyond what we can ordinarily sense. We don't have sense net knowledge of atoms. So we have this equation. What does it mean? So we don't want just a logical system of manipulating the equations. We want to understand physically what the equations tell us. So two ways of thinking about these things. Okay. I've gone a little bit over. Any questions?
Actually, yeah, with guiding wave.
Is it quick? Because I want to let the class go.
Yes, sir. Yeah, I want to ask you.
Okay, so I'll answer questions after class. So we got one more homework due on Wednesday, and there's a test on chapter 1. And the test is about these sorts of general things, the different kinds of experiments that are done, these things that I've covered here about different things to remember, and the ways of thinking, imperiological versus physical ways of thinking. Broad things from chapter 1. Okay. There aren't going to be any detailed calculations like the first two problems on the homework today. But I want you to study the solution and understand if you could do it, how to do it. Okay. All right, so we'll see you in.